Okay. So look at the audience. I expect at least a dozen new SDKs by about next year. And that's because, so we start with the Beam Vision. And the Beam Vision is to provide a comprehensive portability framework for data processing pipelines. And you want to be able to choose the language of your choice and then run it on the execution of your choice. And by language of your choice, this also involves libraries of your choice, ecosystem of your choice. Really, when you choose Python, you're choosing SciPy and NumPy and TensorFlow and all these other libraries that you want to be able to deal with. And currently, we look kind of like this. So we've got Java, we've got Go, we've got Python. They're relatively mature SDKs. You have Nesson SQL DSL and also Shio that was demoed earlier. And so this is kind of, where we are now, and this is where we want to be. Where pretty much you can just pick wherever, whatever, and it just runs. And it might take us a while to get there, but hopefully this talk is a step in the right direction. So yeah, we got OCaml that you guys were talking about. So you're on it. So what exactly is an SDK? So the SDK is the library that is used by the user to construct Beam pipelines. So when you want to make a Beam pipeline, you pick up an SDK, and that's how you construct your Beam pipeline. It's also the library that submits that pipeline to a runner. So you need to take your pipeline, wrap it up in a description, and submit it to a runner in a way the runner understands. And then the third component of an SDK is it provides support for actually executing the user functions. So the pipeline consists of a bunch of user functions and built-in functions, and then you want to be able to actually execute those functions on the worker. So you also have this service where you say, I have this function, I have no idea how to deal with it, but the SDK knows how to do it, so you have to provide this backend as well. So the other thing that an SDK is it's an idiomatic interpretation of the Beam model in a target language. And idiomatic, is hard to pin down. Go is very different than Java. Python has made some choices. We may evolve those. And so depending on the language you have, there are certain constructs that are natural. There are certain constructs that are not natural. And you really want the person to feel at home when they're using that language. So there's also this notion of a DSL. And in Beam, we kind of have a DSL is different than an SDK. So an SDK speaks directly to the runner, and it provides kind of the whole Beam model, the concept of P collections and transforms and windowing and so on. And a DSL is typically built on top of an SDK, and sometimes it provides a subset of the model. Possibly, there's lots of cases where when you subset the model, it's actually easier to provide a consistent user interface. It's easier to provide support. Possibly, you can guide the user more directly into the path that they want to go by cutting off options. And some of the examples we have here is SQL and Shio. And that doesn't mean that it's really an either-or thing. You can kind of have a mixture of both. But right now I'm going to be talking about a little bit more about SDKs than DSLs. So constructing a pipeline. This is the first thing that an SDK has to do. And it's actually not too bad. So you basically have a notion of, you have to introduce a notion of P collection, a notion of transform, and you just have to keep track of what the user did. So when the user has a P collection, they apply a transform, you return some new P collections that are just pointers back up to what happened. It's this deferred graph of operations. One of the complications is that P collections may have multiple producers. So for instance, you have the count operation that has a group by key inside and a sum by ones inside. Well, that output of the count operation is also an output of the subtransforms. So you need to handle this nested scoping. And this is pretty easy. So now you have your kind of graph of operations. And these are some of the operations you need to be able to do. So there's parallel do. This is also called map or flat map. Parallel do is kind of the workhorse. You have to worry about side inputs, multiple outputs, state and timers, splittable do fun. And you can kind of start off with just the very simple, parallel do, and then kind of extend from there as you grow your SDK to support all these further rich features. You need some kind of a grouping operation. So a group by key or a group by field or whatever your SDK represents the grouping operation as. You need a window into. Some might say, well, if I'm just going to do batch, why do I need window into? But it's an important part of the Beam model to be able to at least track, if everything's in the global window, have at least some motion to say everything's in the global window, so that when it comes time to add streaming, you don't have to throw in an entire SDK. You really need a way to be able to track what is the windowing information for a P collection. You need I/O. You need to be able to read and write something. This can start with just text files, but actually, will grow into being able to read and write lots of different things over possibly distributed file systems. And then the other thing is you want to be able to provide user-provide composite operations so that the user can package up their sequence of operations, like count, and package it as a single thing for the user to use, for other users to use. Some other expected transformations: create. Create is just is an I/O where you provide something in memory. Flatten, where you have multiple P collections, you take the union. You probably want to provide some kind of a join or a co-group by key. And combining operation is also a very typical operation to have. And then you also, we have support for metrics and counters and pipeline results, or some other kind of things to take into consideration. I/O. So I don't know, how many of you went to the splittable do fun talk earlier? Yeah. So if you go to the splittable, if you look at the splittable do fun talk, the idea is that I/O is just a do fun, but it happens to be a do fun using all these advanced features. One of the features is being able to pause processing an element and give part of that work back and then continue on your way. And so when you write I/O, you don't actually write an I/O, you write do funs, and you support splittable do funs that can dynamically split and process elements. Similarly with syncs, syncs are just do funs. They're just do funs that have to be really careful about when you're dealing with an external source, making sure that your interactions with that external source are idempotent. And so your sources and syncs are just do funs that are typically wrapped in these P transforms, so the user doesn't have to look at the insides. Another consideration when you're doing an SDK is coders and types. So we saw this a little bit with Scala. The more that you can infer in your coders, the better off you are. And some languages have more or less capability to do introspection on the types. And you need, whenever you have types, you have to understand the types. How do you serialize this? If I have elements that are strings, how do I get those strings to a remote machine on the other side of a shuffle? You probably want to have some kind of inference. You probably want to have some kind of registration. And also another thing to take into account is if you're using these for keys, you want to have deterministic serialization, which some libraries don't provide. The other thing is there's some standard coders you have to provide. So you need to provide a KV coder. You need to provide a coder for iterables. You need to provide this length prefix coder, because there are some times when you send the data to the runner has to be able to interpret what you have, and maybe pick apart the pieces, like pick out the K of a KV pair to be able to do grouping. But there's a small number of standard coders, and then you can kind of do whatever you want according to the types of your language. Another kind of very language-specific thing is how do you represent your user functions? So are these just like pointers to functions? Are these full-fledged classes? Are they lambdas? Do you have first-class functions available? If you have first-class functions available, well, how do you package up and serialize them? Or are they just these ephemeral things? Another thing is a lot of user functions are not just the function, like the map method, but they have other functions associated. So like a full do fun has start bundle, finish bundle, setup, teardown, and other operations, timers that are kind of, you have multiple methods that are grouped together as one unit. But you also want to make simple things simple. So if I just want to map x to a pair of x and 2 times x, if your target language has lambdas, maybe you should just accept a lambda in that case. Calling conventions. So as well as being able to have all these other methods, when you process an element, maybe you have other contexts. You want to say, well, I'm processing this element, I want access to the window. I need access to state. And so there's some considerations there in making that nice and kind of language idiomatic, and also performant. So in Python, we actually special case the case where you only have one argument and make that really fast because that's common. In Java, they actually went down and did bytecode generation because the reflection was way too slow. So this is something to take into account when you're doing an SDK is how am I going to make this fast but also natural? Another user function is composite P transforms, but those actually don't have to be serialized. They don't have to be efficient because they're executed on the user's machine, and the results of those executions are sent over. So this is more about combine funds, do funds, and so on. Another thing that you might want to have, but this is not necessary, is a direct runner. So when you're debugging your pipeline, it's really nice to be able to get your error and to be able to attach the debugger that is natural to your language. So if I'm in C, maybe I want to be able to attach GDB and understand what's going on. And but before you have a runner, what you can do is you can bootstrap with the universal local runner. So we have a Python one and a Java one that speak the fun API and the runner API. So that way you actually don't have to implement any execution at all. You can submit your job to the local process on your machine, which then turns away and processes the job and gets back. Lots of times you want to have a direct runner because this makes it easier to debug without having to start up separate processes and so on. And Go went this route, for instance. They have a direct runner for very simple pipelines. And if the pipeline is complex enough, like it does advanced windowing, they say, I don't know how to do this, but I'll just do the more complicated thing of starting up a subprocess to execute the pipeline. So that brings us to the runner API. So the next thing you have to do is when you have your pipeline construction, you have to submit this pipeline to the runner. So what's the definition of a Beam pipeline? So we have a bunch of protos that are sitting in the Beam repository, and kind of you can think the way the protos is structured as a pipeline is a set of components. You have a root transform, which is kind of like the pipeline itself, and it has subtransforms, and those have subtransforms. And it's just this big list of transforms, and everything is a reference. So you have, for instance, for P collections, they reference their coder. Coders might reference other coders. So kind of when you look at the protos, everything is just a dictionary, and they have these string references to everything else. The other thing is you have this notion of URNs and specifications. This is kind of like the other kind of big thing when you're reading the proto files to understand is these URNs specify exactly what kind of a transformation it is or what kind of a coder is. And depending on that URN, it may or may not have a payload, which is just a binary blob interpreted according to that URN. So an example is probably the best way to do it. We have this group by key operation. And it might be in your big list of operations and say the 10th operation in your pipeline is group by key. So you have this URN right here, which is just group by key. This is a standard URN. And there's no parameterization of this group by key. And then you list, OK, my input is this P collection. This is a reference to a P collection. And somewhere else in this file, you'll have P collection 1 has coder X, has windowing strategy Y, is not bounded. And same, this is my output P collection. Then these are local names. The group by key doesn't use the local names, but they become more important for things like parallel do. And so let's look at parallel do. This is probably the most complicated one. And once you wrap around your head around the parallel do, it's not actually, everything else is pretty easy. So here we have a standard parallel do transform. So you say, I'm a parallel do transform, here's my payload. Now, if I was actually to look at the payload is just a binary blob. But because I'm a pair do transform, I know my payload is this particular proto. And in the Protos files, it says, whenever I use this particular URN, this identifier, my payload is this. So what's the payload of a parallel do operation? Well, you have a do fun. Look at that. Do fun has a URN. This URN might be language serialized function. Or it might be the standard pair with one operation. It has this should be payload. It has a payload, which is some binary data that your SDK can understand. And then the key thing is it has an environment that says, well, whenever you encounter one of those and you don't know what it is, you can fire up this environment and ask it to execute it for you. So this is the do fun. You have side inputs, you have state specs, and so on. And then you have your list, just like before, of inputs. Your side inputs are normal inputs. And you have your possibly list of multiple outputs. So all of the entire pipeline is just basically structured like this. Probably the easiest way to do it when you're trying to bootstrap an SDK is to look up Python or look up Java, just dump these protos out and inspect them and just do what it does. So there's another thing. I'm going to skip over this. There are special URNs that runners have. So for instance, for combine, it's really often that you want to be able to lift this above the shuffle. So there are special URNs that you have to kind of know to use. So let's look at the jobs API. Now that you've defined your pipeline, you might want to actually run it. So here, we submit a job. The SDK is used to build up a pipeline. We build up our entire pipeline, and then we start up a runner. And so there's a lot of ways of starting up this runner. For instance, you could start this runner by manually starting up a Flink cluster. Sometimes the SDK could have some stuff that starts up this runner. The runner might be a hosted service. But whatever the runner does, it has a little job service port. So you connect to the job service, and you say, here's my pipeline. This is in the there's same models directory. There's this protocol here. The other thing you need to do is you need to upload your artifacts. So you say, whenever you're running this pipeline, you need to have available this jar file, these image files, some data files, and so on. So these are all uploaded to the runner. And then you say, OK, now you have everything you need. Go and run your pipeline. And the runner will take the pipeline, break it up into chunks that it knows how. These are runner-specific chunks, and go off and execute your pipeline. So let's look at how the pipeline is actually executed. So the fun API is actually the most complicated part of the API, because this is the API that actually has to be high performance, but at the same time has to interact with your SDK, which might be in a completely different environment than the runner environment. So there's another here in model fun execution is where all these protos are defined, and there's 4 basic protocols involved. There's the control plane, and this is where you say, OK, here's some work for you to do. There's the data plane, And the data plane is actually a streaming API where you asynchronously push data on the data plane, and the SDK asynchronously pushes it back. This is so you can avoid a huge amount of overhead that would be incurred if you said, here's an element, okay, here's another element, and so on. There's the state plane. This is the corner of a poll API where you're running along and you say, oh, I need some more information, like I need to know what my state was before, and so you can actually fetch it. So this is a push API, and this is a pull API. And the fourth API is logging. So all the information is logged, and you can push your logs back to the runner so the runner can do something intelligent with them. There's some other APIs, if you look at the slides, for if you're not using the bootstrapping scripts. So I guess I kind of went over these. So the runner API, the control plane, it pushes a stream of events to do. So it says, please process this bundle. Please register this bundle. And these events are asynchronous. And what happens is whenever it pushes an event, it's tagged with an ID. And then it just waits for a message that has that ID as the response. So it's kind of like a normal RPC, except for it's streaming to account for the high throughput. The primary thing is process bundle, which is like, actually do this work. And the payload of a process bundle is a reference to a process bundle descriptor, which is a fused graph. So when you write an SDK, you not only have to process your do funds, you have to be able to accept a possibly fused graph of do funds. And this is so that you can avoid this high overhead of going over the boundary back and forth. And then errors are returned along this as well. And for Flink and possibly other pipelines, we're still detailing the spec, you have to be able to process an unbounded number of requests in parallel. So this might put some constraints on, you have to be very multi-threaded in your SDK. The data plane. So it's a multiplex stream of all your data. So you typically open up one data connection, and then you push all your data for all your inputs and get all your outputs back on that same plane. And this is, again, it's multiplexed, and you have one stream to support high throughput. And so and you kind of package things into chunks. You throw chunks over the wire, and it pulls out the chunks and then gets the chunks back. And I'll show this with a picture. State plane, as I mentioned, is pull requests, where the SDK wants to request information from the runner. And then logging is when you want to log information. For instance, if the user is using the logging API that's standard to the language, like Java logging or Python logging, what you typically want to do is you want to redirect this logging, or at least copy this logging, out to the logging API so that the runner can have access to this information as opposed to being, say, in some standard error log, sitting in some JVM, sitting in some Docker image on a remote machine. So let's look really quickly at how this works. So the runner is ready to run a pipeline. And the runner starts up a whole bunch of workers. And let's look, we're going to just focus on one of the workers right now. So first worker starts up a bunch of services. So you have, I don't know if these are too small to see, a control service, a data service, a state service, and a logging service. And then it says, I'm going to look at my pipeline, and looking at this little green bit. This green bit is user code that I don't understand. And I'm going to fire up the appropriate worker for that green bit, looking at the environment variable. When an SDK worker is fired up, it connects to the control plane and gets some data. So we'll get something to run. Stores that away, and then it says, oh, now when I'm looking at that, I need to open up a data plane. So now this is initiated by the SDK worker opening up a data plane, and you can start sending data along this data plane. Notice I'm sending this data even before I have started running this worker. So now what happens is the data comes along the data plane, and the SDK worker pulls out the data, plumbs it through its graph, and then returns results along the same data plane. Now, while this is going on, you might say, oh, I have another bundle. Please execute this bundle as well. And the SDK says, I can do that, and it can execute a whole bunch of bundles in parallel. So you have all this data going along the data plane. These messages have elements from various different operations. It multiplexes them, processes them through these runners, comes back out. The runner might request progress. So I can say, how's this bundle doing? And you respond with, whatever. There's some standard progress messages for every bundle. Likewise, some things might require inputs. So this state right here might say, I need to know some state that didn't come along the data plane because it's infrequently accessed. So you open up this channel to the state API. The actual state API to open up is information that is encoded in here. It should be noticed that these are separate because the data service and the state service and logging service can actually be elsewhere. So the runner might say, throw your logs over here, get your data from over here, and I'll tell you what to do. Right now, usually this is all co-located, but we've made this more flexible. For instance, you might have another SDK worker in a different language, and they communicate along a channel there to do their work. So here's some state. It says, here I want some state, and it gets a state request back. And then all the while, you're logging stuff along this logging channel. So that, in a very compressed nutshell, is the worker fun API. So when the workers are done, one key point is that currently, you just send an empty bundle to indicate that the channel is closed. And when the channel is closed, you respond with, well, possibly it was an error, but typically, success, I'm done with this bundle. And when all bundles are done, the runner closes the control plane. That causes the SDK worker to clean up. And then, well, the runner usually kills the SDK worker. Of course, in a streaming pipeline, this will stay up indefinitely. But for a batch pipeline, this is how you tear it down cleanly. So now let's close the loop back to the job API. So while the runner is, of course, processing things, every runner worker is publishing up to the runner master, publishing up to the runner. And then this runner is publishing back on the job service the status of the pipeline. So the pipeline is running well. Here's the number of workers. By the way, here's some counters, some elements. And then the SDK may choose to publish this information back to the user. So that's kind of how the whole thing works. So in summary, the SDK client is used to build up a representation of the graph and then compiles it into a language agnostic runner API representation. This runner API representation has these little payloads that may be language specific, that only the SDK knows what they mean. You know, serialized Java bytecode. And then it sends this information along the jobs API to a runner. And this runner then fires up the workers according to the environment specification, uses the fun API to actually execute the code, and status is plumbed all the way back up this channel to the SDK client. So, any questions?
I actually have one.
Yeah.
I'll go first. What if the runner master dies? Like, what happens usually?
Yeah, so that's totally dependent on the runner. So runners have different capabilities of like doing a master election, or you know, say all the workers die off if the runner dies. So yeah.
Okay, so that's totally up to the implementation.
So it's totally implementation detail of the runner, and in a lot of cases you can view the runner as a single black box, and really it's like this very massively complicated, you know, multi-process thing.
So there's probably like a backup running then usually, or
yeah,
it
yeah.
replicates. Cool.
Yep.
Any other questions?
So do you still call it master slave?
What?
Do you still call it master slave, given that Python has eliminated?
We call them SDK worker harnesses and SDK runner harnesses, technically. But yeah.
So I have a question. What's an impulse step in the information?
Okay, yeah, so that's a good question. So when you're doing a read, reads are really pardoos. And the question is, well, how do you launch this pardue? And so an impulse is a special primitive that says, when you start your pipeline, I will give you exactly one void element along this pipe. So an impulse is a special primitive that always produces exactly one element. And so a typical read, for instance, will say, whenever I get, it's just a do fun that says, whenever I receive an element, I'm going to spit out all the elements corresponding to my files. So that's an impulse kind of kicks things off. And then from there, you can have your modular I/O continue.
And, is that something to be cognizant of when you're writing a new SDK?
Yes, so when you're writing a read operation, it's really the only way to represent it importably is an impulse followed by a do fun that actually does the reading. Yeah.
Great talk, thank you very much. I was wondering, since implementing a new SDK is not exactly trivial, as you showed us, and especially implementing against the fun API is, I guess, quite tricky. Is there a plan to have like a test suite or something like that to programmatically execute your SDK harness implementation against?
Yeah. So actually, we're hoping with the Fun API, it's actually easier to implement an SDK. But if it's not easier, at least it's more well-defined. And then what happens is there's a universal local runner, which runs locally on your machine. And your SDK can submit jobs to it. And then it will kind of like do the whole orchestration and execution locally. And actually, one of the modes of the universal local runner that we're talking about is actually where it will push the corner spaces, like push out to all the corner spaces and dark corners of the spec. So for instance, instead of just like executing your do fun once, it might like execute your do fun 3 times in a row and then throw away the results and then execute it again. And all sorts of crazy stuff like that. Mix up the order of things to try to force the SDK and actually your pipeline logic in general to understand how this might run in a truly distributed environment. And so this universal local runner is shipped with the Beam itself. And so when you're writing an SDK, you can kind of write it against that universal local runner, and that will then give you confidence that it runs against all these other runners that match the spec. So yeah.
Cool.
Yeah, so when the SDK worker is requesting state, and you have a situation where state is relatively large, how does it do that efficiently?
Yeah, so the state is at least, so it's parameterized, once again, by a URN. So you say, I want this type of state, and depending on the type of state, it has a payload that specifies that state. And the one state we support is keyed state. So the payload is, I want this state for this window for this key. And so if you have a multi-map, for instance, you can request just exactly one item out of that multi-map. Okay. Yeah, so that's very important for a lot of jobs to have very large state. You might want to only tweak a little part of it or look at a little part of it.
Cool. Thank you so much, Robert.
Yeah.